So I like to always, ask my students if they can prove that I tell them the Earth is flat, and you will fail unless you can disprove me in cosmology class. And I'd say a lot of them can prove it, but a lot of them can. Almost none of them can prove that the sun is not the center of the solar system, or is the center. I say it's not the center. I say prove me wrong. I say prove the Earth is not the center of the solar system. So all these things, I would say 0.1% of the human population can prove that the Earth is orbiting around the sun, not the other way around. Because that's the way it looks, right? Earth looks flat. Earth looks like it's being orbited by the sun, not the other way around. And certainly the moon orbits around the sun, so why not the sun? The moon orbits around the Earth, so why not the sun orbiting around the Earth too? So what is most surprising there? Why do we know? How do we know about it? It comes down to geometry. So the link between geometry, which is the study of math, but actually the geo in geometry means Earth. So the study of the Earth led to the study of mathematics that we now associate with geometry, and then of course higher geometry like general relativistic geometry, even higher dimensional gravity, objects like string theoretic things, membrane theory. Those all come from geometry, which is measurement of Earth. So the measurement of the Earth led to the notion that the Earth is a sphere, or very close to a sphere. It's not a perfect sphere, but it's very close to it. And then going at different distances on the Earth's surface allowed us to make measurements of the distance to the moon. But not only that, Galileo actually estimated the height of the mountains on the moon, which is very crucial, through a telescope from the shadows that were cast at different times during a lunar year, which is the Earth month. So one complete revolution around its illuminating, or the body that it orbits around, is called its year, or synodic period, which is the moon's orbital period. So he was able to measure the height of the mountains to within a few kilometers of what their actual value is, just with the crude telescope that's no bigger than the lens on a camera, a DSLR camera. So this is incredible that he was able to do that. And then once we go to different places on Earth, the parallax effect allows you to show that the distance that it is away and where it is on Earth. And that's actually how we mapped out all the different geometries of our solar system.
But so this is like the original assumption is that space is this three-dimensional Euclidean thing that happens here in front of us and also at the moon.
Yeah.
Because otherwise, having never been to the moon, they had to make that assumption.
Right. So a lot of the early prehistoric notions of the geometry of space-time, as you might say, came from incorrect assumptions that had some kernel of truth. So Aristotle, for example, thought that heavy things fall faster than light things. So if I take this, very nice swag mug with the logo pointing your way, I won't show you my swag. And I take this real Nobel Prize medallion that I got from Ray Weiss.
Oh, really?
Right? Yeah. So these are much lighter, even though this is made of solid gold and milk chocolate. So if I dropped them, they would go at different rates. But Galileo said, "You idiot, Aristotle, just put one on top of the other, and you can prove that they fall at the exact same rate." But he had a kernel of truth. They're all attracted to the Earth's center. So once you had a radial direction, that started to map out that there are different positions in space in the third dimension, which we can't see. We don't see depth. So we look at the Andromeda Galaxy, it's 6 times bigger than the full moon's diameter. So if things width determines their proximity to us, we'd say, oh, it's got to be 6 to 12 times closer than the moon is. But it's actually 2.3 million light years away from the Earth, not 250,000 miles away from the Earth, light seconds, 1.25 light seconds. So Galileo kind of started to disabuse people of the notion of the Earth being the center, but there was always a notion of 3 dimensions, that you could go places on land, you could go places by sea, you could go at great distances, and if you had a tall enough, tower, that you would see things farther and farther away. And that's another thing that Galileo did. He didn't invent the telescope. Actually, Dutch invented the telescope. And they had access to the finest crystal, and they were traders, so they used their merchant economy. Capitalism. Sorry guys, capitalism is one of the best inventions on Earth. And I'm just joking. Capitalism led them to be not only a military power, but an economic power, which led them to be a scientific power. So what they were able to do is collect the best glass on Earth and make the best ingredients for telescopes. They never thought, though, to take the telescope and point it up at the sky. Galileo did that first. He made pictures of it, and then he started to discover you could see things farther away with a telescope. Could see things on the moon. That implied that the moon must be extremely far away. And then they measured it over the year. Actually, they knew the distance of the moon before Galileo, to within a couple of 1,000 miles. But that was pretty good.
So the spyglasses were before that, right? For traveling purposes, and then he was the one who
they were literally for
figured out to look at it.
Spinoza was grinding glass.
That's right. Yeah, Spinoza was a lens maker by day, and then he was a heretic by night. And he was kicked out of his synagogue and kind of banished. But then he lived to influence, or his life influenced Einstein to have the notion of this kind of pantheistic God that Einstein would later champion. So Spinoza's God. Yeah, exactly. Spinoza. So the Dutch had that, and it was known for a long time that the Earth was kind of either the center of the universe or it was in the universe, but it wasn't like there was just some dome affixed to which were stars, planets, and other objects that they didn't know much about, like comets and physics. But the actual amount of depth perception they had was minimal. Even Galileo, as brilliant as he was, he thought comets were in the Earth's atmosphere. In other words, he thought they were atmospheric phenomena, like the meteorites that I gave you, and I will give to you out there. So you want to look at it. If you have a .edu email address, I give these away, briankeating.com/edu. And you'll get an actual meteorite. And those are a phenomena that are in the atmosphere. They come from asteroids, fragments of them burn up in the atmosphere. Galileo said, well, a comet's just like a really slow-moving meteorite. But of course they're not. They're in the solar system much farther away than the orbit of the moon. That was also discovered by trigonometry and what's called parallax. So yeah, that's how we start to map out where our position is in the universe.
Do you have a favorite answer for why, or proof for why the Earth isn't flat? Like, has any one of your students ever written something that's extremely original?
Not about why the Earth is not flat. I think they're all comfortable with that. They can kind of figure that out on their own, and that was known really since like 2,500 years ago. Aristarchus. Yeah. But proving the Earth is in motion was not proven until the late 1700s, early 1800s, when they noticed what's called parallax, or stellar aberration, rather. So if you look at a very distant star, as the Earth goes around the orbit with respect to a very, very distant star, you'll see the trace of the pattern of the star will map out a little ellipse or circle, and that's indicative of the fact that we're orbiting around the sun. There's a slight parallax shift between us and that star, even though the stars are at huge distances from us. Even the Earth's orbit, the orbital distance between 93 million miles, 186 million miles across, that's enough to get enough parallax to see that stars will make a little circle as we...
Relative to what? Relative to
more distant stars. More distant stars.
Oh, even more distant stars.
Yeah.
Okay.
So closest star, Proxima Centauri, is 4 light years away. You look at something that's 10 light years away, that'll be almost exactly, or half the parallax or less. So you'll be able to see its motion as kind of cosmic wallpaper, in which you can see things moving in relative motion. So people knew that for a long time. But it took a lot of thought to think about that, because it's actually, the effect is made more prominent by the speed of the Earth's orbit being a fraction of the speed of light. If it was much, much slower or much, much faster, you'd have different results. It'd be harder to prove that we're in motion. So most people get that wrong. But I don't use it for a final extent.